And now it's my pleasure to introduce the next speaker. We'll move from rather public health issues to more specific topic, which will be covered by Tomas Hajek. Tomas Hajek received his PhD in neuroscience from Charles University in Prague. Later on, he joined Department of Psychiatry at the Dalhousie University in Halifax in Canada, where he became associate and later on full professor. And his research interest lies in investigating effects in various clinical variables, including genetic predisposition, illness burden, comorbid metabolic disorders, and exposure to medications on brain structure, particularly in patients with bipolar disorders. He published a lot of in extenso papers in prestigious journals such as Molecular Psychiatry, American Journal of Psychiatry, Biological Psychiatry, and so on. And now he will cover the topic answering the question, my parent has bipolar disorder. Am I at risk? What are brain imaging and clinical studies of bipolar offsprings from their team? So, Tomas, the floor is yours.
Thank you very much for the kind introduction, and thank you for the opportunity to share some of our data with you in this wonderful setting. Now, I'm the last person before the lunch, so that's always difficult, and I'll try not to keep you too long, but it's still better than being the first person after the lunch. So let me first put things in a bit of a perspective. As you know, our brain is the most complicated matter in the known universe. And if the brain was so simple that we could understand it, we would be so simple that we could not. So we may never be able to breach this philosophical boundary, but the hope is that with the advent of new technologies, such as brain imaging, we may be able to get really, really close to it. And this has, to some extent, happened in psychiatry, where brain imaging has really advanced our knowledge about psychiatric disorders. However, as a clinician, I need to admit that the impact of brain imaging on clinical psychiatry has been next to nil. And we can debate the reasons for that. We can blame the complexity of the brain. We can blame the fact that the technologies have their limitations and haven't been around for that long. But I think that the main problem, actually, why brain imaging has not informed psychiatry is related to the fact that clinical psychiatry has not sufficiently informed brain imaging. I'm talking about the clinical heterogeneity, which is a bread and butter of every clinician, but it is often ignored or paid only lip service in brain imaging studies. And clearly, until we have very detailed clinical descriptions of the patients that we're studying, we won't be able to correctly name the phenomena that we observe through the lenses of MRI scanners. Let me give you some example of the heterogeneity. Now, here you can see a meta-analysis looking at amygdala volumes in bipolar patients compared to controls. Now, you can make very similar arguments for any other brain structure or for any other neuroimaging modality. You can see here that some studies showed smaller amygdala volumes in patients relative to controls. Many studies showed comparable volumes between the groups, and some studies even found larger amygdala volumes in patients than in controls. So there's clearly a marked statistical heterogeneity of results, which likely reflects the clinical heterogeneity. Now, if you summarize, if you add up the negative effect sizes with the positive ones, then it's not surprising that you end up with essentially no difference. So if you simply ask yourself, are there brain changes in bipolar disorders, you would have to say no for most of the findings. But that's not a very satisfactory answer, because that would ignore the individual studies which did find differences. So it seems to be more pertinent and more interesting to ask ourselves which clinical variables underlie the neuroanatomical alterations in bipolar disorders. You see, the problem is that brain changes in patients with bipolar disorders may have several different origins. We know that the illnesses, that bipolar disorder runs in families, that the familial aggregation is mostly related to the genes. And what the genes do is that they alter the structure of the, or function of the brain in a subtle way, which increases the risk for development of the behavioral manifestations, which we call bipolar disorder. So some of the changes that we observe in the brains of our patients reflect the genetic susceptibility and represent the biological risk factors or biomarkers or endophenotypes of the illness. But that's not all. We also know that the illness exerts negative effects on the brain and that it leaves a sort of scar on the brain. So some of the changes start occurring only later in the course of the illness and are secondary to the burden of the disease. We also know that comorbid conditions are more a rule than an exception in bipolar disorders, and many of these comorbidities also have their signature, which they stamp on the brains of our patients. And last but not least, the treatments that we use, not only the biological ones, but also the psychotherapy, alter the very hardware or wetware of the computer that we have between our ears. So considering all these sources of changes, I would say that it's not difficult to find brain structural alterations in bipolar disorders. However, only the primary changes actually have diagnostic significance. The secondary changes, for example, the burden of the illness, they tell us about what the patient went through or which comorbid conditions the patient had or which treatments he has been exposed to, but that has very little diagnostic relevance. So if we want to identify diagnostic markers for the illness, we need to try to minimize or fully eliminate these secondary changes so that what's left is only the primary alterations, the endophenotypes or the biological markers. How can we do that? Well, ideally we would want to study people who do not have the illness, are not treated with any medications, but they carry the risk for the illness. And how can that be done? Here's a little hint. As I mentioned, mood disorders run in families, and family history is the strongest risk factor for bipolar disorder. So one could study that the risk is particularly high in monozygotic twins, but those are difficult to get. It's actually enough to study first-degree relatives who have substantially increased risk of developing the illness relative to general population, about 8 to 12 times greater risk. So there is a research design which is called high-risk design, which does exactly that, where you study the affected and unaffected offspring of bipolar parents to eliminate some of the confounders related to the illness and focus better on the actual biological signature of the disease. And this is what we did. Initially in Halifax, this is one of the families that contributed to the data. As you can see, there are multiple affected subjects, those with the black marks, from multiple generations. We're now recruiting from this generation here. Subsequently, I was lucky enough to continue collaborating with my colleagues in Prague, so we added a parallel arm of the study in Prague, using similar methods, but on a very different sample, obviously. And so having these two arms of the study allowed us to use what's called replication design, where we ran the analysis in each side, and only changes that were replicated in both sides we considered as true positives. Now, as you know, replication is the best way to differentiate between true and false positives, and we have a big problem in brain imaging in terms of false positives, so we didn't want to contribute to that. This replication design goes against an old research maxim, which says never, but never attempt to replicate a successful study. So most of the times you end up with nothing. However, if you do replicate your findings, then you are likely on to something. You are likely finding something that's real. And I was very excited that we did have a replication that specifically the affected as well as unaffected offspring of bipolar parents in both Halifax and Prague showed increased right inferior frontal gyrus gray matter volumes, which is depicted on these pictures. Now, interestingly, in each side, the differences between the groups directly overlapped, and between the sides, they were very closely adjacent, just a few millimeters apart. So that's quite remarkable that on 2 different samples, we found essentially exactly the same thing. And I'm 99.79% sure that this is a true positive finding and not a false positive one. Now, you can read more about this in biological psychiatry, where I was excited that other people were interested in this, so it made the cover page there. But to me, the real importance of a study is whether it has any practical implications, whether it can actually help our patients, and whether it could help us solve one of the critical problems in psychiatry, which is early diagnosis of at-risk subjects. Now, the problem is that based on data from us, as well as from other groups, it seems that bipolar disorders tend to develop in stages, that they don't start as such. Offspring of bipolar parents typically initially develop anxiety disorders. Later, in puberty, they tend to have their first depressive episode. And the pathognomic feature of the illness, the first manic episode, is in vast majority of patients the very last stage of the illness to develop. So at each of these preceding stages, the patients would be misdiagnosed as having anxiety disorders or having depression, and the treatment that they would receive would be for these conditions, and such treatment may not be ideal for people who actually suffer from bipolar disorder. The good news is that perhaps we can use these stages for prognosis, and that's what we tried in our sample, and it worked to some extent. We saw that offspring of bipolar parents who suffered from anxiety disorders as children had about 2.6 times greater risk of future conversion to mood disorder than offspring of bipolar parents who did not suffer from anxiety disorder. And what was interesting was that the anxiety disorders preceded the conversion to mood disorders by an average of 8 years. So this is quite good, and this was also confirmed by other groups. So it's good, but maybe it's not good enough. We're diagnosing here based on clinical symptoms. So that means that the underlying pathology is already rather pronounced because it's already penetrating into the phenotype. And it may be too late to substantially alter the trajectory of the illness. It would be much better if we could intervene at the asymptomatic stage before there is any clinical manifestations. And that's where the brain imaging comes in. And so the question becomes, could we use brain imaging to identify subjects at risk for bipolar disorders? And to answer this question, we used the same data and applied a new analytical method, so-called machine learning, which is a pattern recognition artificial intelligence technique, which attempts to identify patterns of distributed small changes which characterize a particular disease state. So unlike the traditional methods, this really works on the level of individual subject, not on the level of group. And when we apply this technique, we were able to correctly classify 69% of the subjects as either being at high risk for the illness or being controls with low risk for bipolar disorders. And this was above the chance level. And it's interesting because these people were completely unaffected. So the machine learning or the structural MRI was picking something up before there were any clinical manifestations. What was even more interesting was that one of the regions which most contributed to the classification of subjects into the at-risk and control groups was actually the right inferior frontal gyrus, same as in our between-group comparisons. So this constitutes another within-study replication with a different method of the same finding and makes the finding even stronger. This also raises other questions, such as, could we use the enlarged right inferior frontal gyrus to identify who among the unaffected at-risk subjects would become affected? Well, this is clearly the more important question. And in our between-group comparisons, not all subjects had enlarged right inferior frontal gyrus volume. It was only these people here. And our hypothesis was that the people with the abnormally enlarged IFG would be the ones who are at a particular high risk and would be the ones who will go on to convert to the illness. And we continue to follow these people clinically, and on average, 4 years after the baseline scanning, we saw that the unaffected at-risk subjects who had baseline enlargement of the right inferior frontal gyrus showed about 4-fold increased risk of converting to mood disorder relative to the unaffected subject who had normal baseline right IFG levels. Now, this was very interesting to me, but it's still very preliminary. Obviously, you need a lot of subjects and a long time for enough of them to convert to the illness. So we are continuing with this study and recruiting more and continuing the follow-up. So stay tuned for that. So to conclude, I hope I've been able to demonstrate to you that not all brain changes in bipolar disorders have diagnostic potential. These brain imaging changes may predominantly reflect burden of the illness, presence of comorbid conditions, or effects of medications. There is relatively strong and replicated evidence that increased right inferior frontal gyrus is found in subjects at genetic risk and early in the course of bipolar disorders, and that the enlarged right IFG is associated with increased risk of future conversion to affected. And I think great hope lies in combining new analytical methods with smart research designs which help us eliminate some of the important confounders. I'd like to thank my colleagues and collaborators in Canada and in the Czech Republic, and thank you kindly for your attention.